Right, so this is section 7.8, improper integrals. So this section is also pretty straightforward. We'll go back into limits way back in the day when it comes to calculus. Most of it is just lots and lots of big definitions when it comes to it. So lots of examples and just big blocks of definitions. Okay, so this is the first part or first type of definition we're talking about in this section is the improper integrals part 1. So this says is if the given improper integral, so remember improper integral basically means it goes from a number to infinity, or vice versa, from like a negative infinity to like a number itself. Right? These are types of improper integrals, or you're going to have from negative infinity to positive infinity. Right? Those are the type of integrals we're going to deal with in this section. Okay? So if we have the first of the types, so if we have a integral from number to infinity of the function, we want to take the integral of that. So as of now, we don't know how to do that, but in this section, we have a very special definition to make us see if we can. And we're going to talk about something very special that's going on in chapter 11 once we get there as well, convergence. So if there exists a t such that if I take the integral from a to that t value, and that does exist for t being greater than a, then we know the integral of a to infinity, so which we wanted to find, is equal to the limit as t goes to infinity of this integral here. So essentially what we're going to have is we're going to plug in a value for t, just like any other variable, and we're going to find the integral of this. And we're going to take the limit and see does it go to a number or not. Okay, that's basically what's happening here. So if it goes to a number, therefore that equals exactly that integral. And if it equals basically infinity, there's no way to actually find the integral, and we'll talk about that in a little bit. The second type is where we have the opposite. So if it goes from negative infinity to a value itself, and same thing, if you can add a t such that now goes for t to be, there exists again the limit as t goes to negative infinity this time of that. Now, both of these we say it converges if the limit does exist. Now, in most cases, right, we'll talk about convergence way down the line itself, but it's a good a brief introduction to what a convergence means. Convergence means basically it goes to a number. Sometimes we won't be able to find that number, sometimes we will, but it goes to a single number. It goes, converges to a single number itself. If both improper integrals do not exist, so if this doesn't exist, meaning it goes to infinity or negative infinity, right, doesn't it go to an actual number, we say it diverges. Okay, so convergence means it goes to a number, diverges, it doesn't go, it just goes on for forever. That's essentially what those properties means. Okay. And then the last type of integral is where we have negative infinity to positive infinity. Essentially, this breaks into both parts. So in other words, unfortunately, if you have the last scenario, we have to do both of these and see does it count. Because one of these actually could work, and the other one actually doesn't diverges. So therefore, the whole thing actually diverges. So that's the reason why this is more work, because we actually do both of these when it comes to that kind of example. Okay. So lots of definitions. What does it mean by convergence, divergence? So most of these examples can literally ask you, does it converge or diverge? So in other words, does the limit exist or does it not exist? And that's basically the question we're dealing with in a lot of these examples going forward as well. And so we cut the next chapters as well. So let's just see what we have here. So we have the first part, right? We go from number to infinity. So essentially we're in this situation. So what we do is we write it. So this is the same thing as the limit as t goes to infinity of integral from 1 to t of 1 over x dx. And then we just take the integral the old-fashioned way. So integral 1 over x is natural log, evaluated at 1 and t. So plugging this in. So plug in t into here, plug in 1 into there, and we just evaluate that. So we know this is 0, so that doesn't do anything. And notice if as t gets bigger and bigger and bigger to, like 5,000, 10,000, 20,000, this again goes bigger, right? It doesn't go to an actual number, right? So if you can just plug in a calculator, like natural log of 5,000, it's going to get a number out. It may not be a very big number, but it's still a number out. And if you plug in 10,000, it gets even bigger. Again, not as much, but it's still growing and growing and growing. So this essentially just goes to infinity. So therefore, this whole integral actually diverges. Just like that. So So that's how we're going to test for convergence or divergence. Essentially see, does the limit actually exist? So this goes way back to the first chapter of calculus you guys have done, right? A review of limits itself. But again, we're not going to get too much in detail of the limits, but that's all we're going to be roughly doing, just taking the limit of the integral itself. So something a little different you guys probably have seen before. Okay. So we'll share a couple more examples in the back when it comes to it. So now, almost like exact same scenario, but now it's just 1 over x squared. So same situation as the first one. Okay, so take the integral, and this should be negative x to the negative 1 power, evaluate at 1 and t. So if we rewrite this, and plug in t, so it'll be negative 1 over t plus 1 over 1, so it just gives you 1. Okay. So if we take the limit, this goes to 0, right? So if you're wondering why this is plus 1, right? So if I plug in 1, that gives negative, and subtract gives you a negative. I mean, a negative is positive. So this goes to 0 essentially. Plus 1 gives you 1. So we know this converges to there. So that's the difference between the first and the second one. The first one converges because the limit went to infinity. This one converges because the limit actually goes to a number itself. Okay. All right, so let's try the next type. So when I have from negative infinity to a single number, what's like part 2 of it? So this is the limit as t goes to negative infinity this time. So now t is at the bottom. Okay. Now if you don't remember this integral, it's just a basic a to the x. That integral is this. So it's exactly the same divided by natural log of the a value, which is 2. And this is evaluated at t and 0. So let's see what we get. So if I plug in 0, that's just going to be 1. This is 1 over natural log of 2, which is just, some number. Minus if I plug in t, this gives me 2 to the t over natural log of 2. Sorry, this is 2. And notice this is a number, but this goes for forever, right? This gets really bigger, 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 bigger. So this actually goes to negative infinity. So this diverges. All right, last one before we go to the second part of the integrals. The last one. And I think it's the most difficult because we actually have to test both of them. Okay. So this is actually broken up as an integral from negative infinity to say 0. And this really doesn't matter, that number. It just has to be a number that's between infinity, which can be 5,000 if you like. I'm pretty sure you want to do 5,000. There we go. Okay, and now we're going to essentially do this B and C for this question. So notice this is a B here, and this is B. This is C over here. This is B value here, right? So I'm going to do them both at the same time because you'll see they're actually going to be the same thing itself. So this is taking the limit as t goes to negative infinity for this one. Plus the limit of t goes to positive infinity of this one. Okay. So if you remember from the last section, the integral of 1 over a squared plus x squared is actually a property. It's tan inverse. So that's the reason why these two are straight tan inverses of each other. So this ends up being the limit as t goes to negative infinity of tan inverse of x evaluated at t to 0 plus the same thing on the other side. Like that. Okay, so now we just evaluate, right? Plug it in. So tan inverse of 0 just gives you 0. This is the limit as t goes to negative infinity. This is 0. And if you plug in t, you just get t plus same thing on the right, roughly. It's going to be t now, and this is going to be 0. Now, as t goes to negative infinity, remember, so you have to look, again, remember back into pre-cal, I guess if you want to call it, inverse of tangent. So, right, tangent goes from pi over 2 to negative pi over 2, but the inverse of it, or the arc sine, right, if you want to think of it that way, flips it to its domain, right? So it's so the range was infinity in regular tangent, so in arc tangent, or the inverse of tangent, is the opposite. Its domain is now from pi over 2 to negative pi over 2, right? So as t goes to negative infinity, this ends up being going to negative pi over 2. So this ends up being negative pi over 2. And the opposite goes over here. As t goes to positive infinity, this goes to positive pi over 2. So adding these up just gives you pi. So therefore it converges. So a little lengthy process when it comes to that one there. Oh, so we keep going. There's one very important integral, just like